A student once asked me, what is the significance of significant figures? I liked the way the student put that question, and the answer is, it all has to do with precision. Here we have a ruler and we're going to be focusing on this side. So we have 0, 1, 2, 3, 4 on to 10 centimeters, and between each of these markings we have millimeters. So as you would expect with a device like this, you can measure down to a centimeter and then down to a millimeter. But after that, between these two marks, you're guessing. No, that's very important. So let's suppose we have to measure the length of this pencil. For now, let's assume that this end is perfectly aligned with the 0 mark here. If you come over here, we see that this end is at what mark? That's 6 centimeters, 6.1, 6.2, 6.3, and it's somewhere between 6.3 and 6.4. So we need to guess, and one guess would be to say 6.35. So let's look at this number. The consensus when dealing with numbers is to say, for example, that this 6, we're sure about this. This 3, we're sure about this. But since this is the rightmost significant figure, the understanding will be that this number has been guessed at. So we say that the rightmost significant figure is the first uncertain digit. And so it doesn't make sense to write anymore. Note that it's quite okay for someone to say that they guess 6.36. Again, whoever reads this will understand that this 6, since it's the rightmost significant figure, is uncertain. However, it would be totally unjustifiable for someone to say 6.3521 centimeters. Such a recording would suggest a certainty down to the hundredth of a millimeter. It's only in the thousandths of a millimeter that you would be uncertain. In other words, your uncertainty would be in the order of the thousandths of a millimeter. So this obviously would be bogus, given the instrument that we have here. Suppose that the ruler had been a little bit shorter. How now would we record the length? Note we'd be sure of the 6, and then 0.1, 0.2, 0.3, so 6.3 centimeters. But if we leave this like this, whoever reads it would assume that this is the uncertain digit, and we're not uncertain about that. Notice it's right here. So it's 3 and maybe a little bit more, a little bit less. We don't know exactly where, so it's not off by much. So we could maybe say 6.30 centimeters. This 0 allows us to convey that the 3 is reliably known. So this 0 is significant. So note now, a 0 can be a significant figure. Here we have a caliper being used to measure the diameter of a nut. Later in this course, we'll look more closely at how a caliper is used. But basically what's happening here is this nut is placed between the jaws of this caliper, and we go looking for where the 0 mark lines up here. And we know that it lines up with 2.1234. So it's somewhere between 2.4 and 2.5. In order to estimate where between 2.4 and 2.5, we come along here and look for where we find a line down here aligning with a line up here, and we see that happens at the number 7 here. And so the way we use a caliper, we say, well, that is 0.07, and so the diameter of this nut is 2.4 plus 0.07, which gives us 2.47. However, we shouldn't actually report this like this, because that would suggest that this 7 is not certain. So this should actually be reported as 2.470 centimeters. Here we have a micrometer being used to measure the thickness of this object. Now this diagram is not too very clear, but let's pretend that we can see it clearly enough. So this is giving us measurements in millimeters. So we have 20 and let's say 21 millimeters. So that's 2.1 centimeters. Now the way we read a caliper, and they do vary, but let's assume that's how this one works, is that we look at this reading and say that this is 1400ths of a millimeter. So that gives us 2.114. And we're pretty certain about the 4. It's landing right on the line here. So we put 0 here. So notice now we have more significant figures. And the 0 here is significant. And since it's the rightmost significant figure, it's the unreliable or uncertain one. In other words, the uncertainty is in the order of the thousandths of a millimeter. By now I trust you're beginning to see the importance of significant figures. So here's an American quarter, and let's suppose somebody had measured its diameter and reported its diameter as 2.40 cm. And let's suppose somebody else measured it and reported its diameter to be 2.430 centimeters. And suppose we have a third measurement recorded as 2.4370 centimeters. It would be reasonable to assume then that this measurement had been taken using a ruler, that this measurement had been taken using a more precise instrument like a caliper, and that this measurement had been taken using an even more precise instrument like, say, a micrometer. Now, it's quite possible for someone to use a ruler and record a value like this, but that would be dishonest. And so the significant figures then allow us to discern just how precise the measurement was. And so now we'll take a look and define significant figures a bit more formally. We turn now to figuring out how we identify significant figures. So the first thing we want to say is that all non-zero digits are significant. So if we have the number 346, well, that means there are 3 significant figures here, 5 significant figures, and so on. Now when it comes to the 0, if it's the rightmost after the decimal point, it's significant. So if we have 24.0, the 0 is significant. Of course, if we have 2.6870, that 0 is significant. The 0 is also significant if it comes between significant figures. So for example, 501, that is significant, as is 2.04, that is also significant. So here we have 3 significant figures, here we have 5 significant figures, here 3, here 3 again. Let's look at another one here. If we have 2.0000, how many significant figures do we have here? Well, we have 3 and 2, 5. This is significant, and this is the rightmost after the decimal point. And of course, then these find themselves between significant figures. So these are all significant. How many significant figures do we have here? Well, we have only 3. These are not between significant figures, nor, obviously, is any of these zeros the rightmost from the decimal point. 1 significant figure. Of course, if I write, no, all of these are significant, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. This 0 is the rightmost from the decimal point, and all the other zeros are then between significant figures. There is, however, an exception to this rule, and it does present us with an ambiguous situation. Suppose we write the number 400. How many significant figures do we have? Well, as a matter of fact, we can't tell. So a situation like this is ambiguous. Because such a number is ambiguous in the sense that we don't know how many significant figures it has, it is poor sense to report numbers like these. This is why we have scientific notation. While scientific notation does allow us to express very large numbers and very small numbers, perhaps more importantly, it allows us to unambiguously specify the precision of a number. So if whoever is reporting this actually means to state that there is only 1 significant figure, this number should be reported as. Reporting this as 4 times 10 squared makes it unambiguous now. We know that we only have 1 significant figure here, which means then that this, since it's the only significant figure, this is not a reliable number. This could be 3 times 10 squared or 5 times 10 squared, let's say. This could also be reported as, and now we have 2 significant figures. So this could be, let's say, 3.9 times 10 squared or 4.1 times 10 squared. In other words, here, with a measurement like this, the actual value could be anywhere between 300 and 500. Whereas here, the actual value is anywhere between 390 and 410. And of course, we could also have written this as 4.00 times 10 squared, in which case now we have 3 significant figures. And now this is the uncertain digit, and so this means this could be anywhere from 399 to 401. So notice how the use of scientific notation allows us to express the precision of the measurement, because it allows us to specify unambiguously how many significant figures we have. So, to be on the safe side in science, all values should be reported using scientific notation. This perhaps is new to you. Scientific notation is important primarily because it allows us to unambiguously specify precision. So this brings us to the end of part 1.